Okay, today we'll take a look at what to expect for Monday, test on Monday, over the material we've covered so far in Think Well material, chapters 1, 2, and 3. Now, also, I use the Think Well exercises as part of your, homework or activities or whatever you want to. It's not really homework when you do it here in class, but the worksheets, those get graded, but also the Think Well exercises, the online problems, I count for your grade as well. So if you have some of those left, you may want to go back and make sure you're done with those by Monday. You can retake them if you need to.
Or even if just for practice. Like, say you got a good score on one and you redid it just for practice, and you got a practice score, would it do anything to it?
I think it will keep the high score, but I have record of how many times you take it and what you got on each time. So in case it doesn't keep the high score, I can go back in and look at that. But yeah, that's some good practice problems. Also, we'll go back through the worksheets and talk about what we did there. But in general, there are 20 problems, and what I will do, each problem will be worth 5 points, and I'll go through and grade. If you got the correct answer, you get all 5 points. If you got the wrong answer, then I look at what you've done. If the only thing you have is the wrong answer, then it's -5. But if you show me at least a little bit, some of the things there won't be a lot of work to do, but most of them there's at least a little bit you need to do. If you make just a little mistake, those darn little things, then I'll give you 4 out of the 5 points. So I kind of figure out, okay, you made 3 little mistakes, maybe that's 2 points off or something like that. So make sure you show me something as much as you can. But 20 problems, we'll go through and kind of see what those problems will be like. Any questions on just the basic format here? Now, time-wise, I do not have a time limit. That will be more of your personal schedule and how much time you have. If you want to start early, like if you want to start at 9:30 instead of 10:30, that's fine with me. I will be in, at 9:30, I am in the LRC room 105. That's, you go into the LRC and walk under the stairway and then take a left. If you take a right after you go under the stairway, you'll end up in the women's restroom. So don't do that. Take a left and I'll be in there. So if you want to start 9:30, or even if you're ready at 10, if you want to get started early, that's fine. Or if you can't start early, I will allow you to work late. I don't have a class after this one, so that's not going to be a problem. We may have to move to a different room. But now I will say, if you have a class at 11:30, I will not excuse you from being late to that class. Okay. The test is designed to take 1 hour. So you need to judge accordingly. Is it worth spending more time on the test and then being late to the next class? So that's going to be up to you. But I will not sign any excused my tardiness. I was taking his test. That's your choice of what's more important. So, okay. Now, those 20 problems, of those, there'll be a few of a lot of different types of problems. Probably the most of any type of problem will be finding the limit. Now I know we didn't start with this, so the order of these problems aren't necessarily going to be what we did first will be the first part of the test and so on. Finding limits, I'm going to group all of that together. I guess limit values. We looked at, well, first of all, we looked at graphs and how to evaluate a limit from a graph, from an equation, from a table of values. That first assignment with the limits, we kind of had a lot of different types of problems with that, and then a couple more worksheets with the limits, limit properties, and all about limits. We did more the algebraic way of calculating a limit. So that's as far as what's the right way to do it. I don't care. What I want to see is that you get the right answer. Whether you graph it and find it from the graph, whether you make a table of values out, or it will be designed more for algebraic manipulation, simplify it algebraically. That's going to be the easiest, or maybe not the easiest, the quickest way to calculate a limit. But if you want to do one of those other ways, you're finding the same value any way you do it. Hopefully, anyway. Hopefully you're finding the right value. But I'm not going to say do it by this way or that way. So that's going to be your choice. We did a lot with the limits, and some of those problems might be something like this. Now that's problem with me making up a problem on the go is not very good here, but let's change that. Okay, maybe this will work a little easier. One of the types of the algebraic simplifying we looked at is like this. And very first thing you do is plug in our x value and see what we get. Well, we'd have 4 minus 2 minus 2, or 0, and then of course 4 minus 4. 0 over 0 indicates there is more work for you to do. In this case, we need to do some factoring. And we found something easy enough to factor. Or at least you did, not me. But x minus 2 cancel. And now we're looking at the limit as x approaches 2 with this expression. As we plug in the value this time, x equals 2, we get our limit value would be 5/4. So that's probably the best approach on these. If you can remember the algebraic procedure, we've got the factoring types, we've got the complex fractions, where you have fractions within fractions, and then we also looked at the square roots, and in that case it was rationalizing the numerator, which in algebra we always rationalize the denominator, but in calculating these limits we have to rationalize the numerator, and working through the algebra it simplifies out. So several different algebraic procedures there. Now we did also look at several graphs. So let's pick out I can't draw straight, but let's see. Pick some x values here. Well, finding a limit from this graph, let's see. I guess we need some y values. What about x approaching -2? What would you say there?
-2.
Okay. Now, in this case, there's no hole, no jump. We have kind of a cusp. Okay.
Absolute value?
So, yeah, kind of like an absolute value, a point, but that doesn't change the limit value. We still have when x equals -2, y equals -2, and the limit from both sides, even though they're coming in from different directions, they still equal -2. Don't forget that little dashed line. Okay. Now, what about when x approaches +2? Do we have a limit value there? Okay, that limit is going to be 3 because from the left, from the right, it's approaching the same value. One small difference in which one, the x approaching -2 and x approaching 2, if we go back and calculate what is the function value at -2.
2.
Well, the
Yeah.
-2, okay. That one would have a solid dot, or at least when I originally drew it, we didn't have a straight point there, but there's no open circle, there's no hole in the graph, so it's understood that is the point when x is -2. What about f of 2?
Undefined.
Okay, that's going to be undefined. But we still have a limit value. The limit will equal 3. What would we say about x equals 2? Or about the function at x equals 2? This kind of takes our limit discussion a little bit farther.
When they're undefined, their denominator equals 0?
Possibly. If we were looking at an equation, that might be what happens here. What else can we say? What else have we talked about when we've been looking at limits?
That's like 6.
Continuity?
Continuity. What can we say about the function at x equals 2?
It's discontinuous.
F of x is not continuous or discontinuous. At x equals 2.
But it's the removable
Okay,
discontinuity?
this one is that special case of removable
Yeah.
because of why?
Because there's a circle and you get undefined.
Okay. There's an open circle.
And it's removable at 3?
The open circle would show up at 2, 3
Yeah.
because the limit exists. The reason that it's not continuous is the function value at 2 does not exist. Now, it may also be, if we had the limit or the function value, if we had a solid dot down here, we would still say it's a removable discontinuity, okay? But the reason that it's discontinuous would be the limit does not equal the function value. But initially we did not have that in there, but that would be another situation. Either way, it would still be a removable discontinuity. The limit exists, but the function value does not equal the limit value.
So, and then the removable discontinuity will be the same, or
Yep.
will it change? Okay.
That would still be a removable discontinuity, whether we define this point or not. Okay. Now, one other place that we have a problem would be what?
4?
Okay. At x equal 4. Now, we have a problem for several reasons there. Kind of ran out of room. We'll just put that right up here. Discontinuous at x equals 4 because of what?
Jump discontinuity?
Okay. Jump discontinuity. And more technically speaking, that's because the limit as x approaches 4 does not exist. On the left side it goes here, on the right side it goes here. Another reason, f of 4 is undefined, so just like we saw here, okay. And of course, if the limit doesn't exist and the function value is undefined, then the third condition, the limit value is not going to equal the function value. So that has major problems with continuity. But any questions? Yeah.
Piecewise function.
Okay. Yeah, we'll look at that. Any other questions about the graph and kind of either limits or the continuity?
Are we going to have to sketch graph?
Are we going to have to sketch a graph? As far as sketching a graph given certain conditions, I don't think I have put any of those problems on there. I think we had plenty of other problems that out of the 20. So, okay, so now as we move to the concept of continuity and discontinuity, we looked at not just the graphing, but also piecewise defined functions. So we'll take a look at that next. And we'll just define, I'll make up something here. Five minus 2x with x being less than 1. 3x with x being greater than 1. And let's see, let's go 0 with x equals 1. Well, with this graph, or with this function, I should say, really the only trouble spot would be x equals 1. Is it continuous at x equals 1? If not, is it removable discontinuity or is it a jump discontinuity? Well, to tell that, first of all, f of 1 is defined. That's going to be what?
0.
Okay, that's this part here. Okay, so we will have a point defined for x equals 1. What about the limit? Limit as x approaches 1. Well, technically, we'll need to break that into two parts. Look at the limit as x approaches 1 from the left, and the limit as x approaches 1 from the right. Now, what are we going to be using for x approaching 1 from the left?
The top one.
Okay, the top one. x less than 1 would be x approaching 1 from the left. So we can say f of x will specifically be this formula for those x values. So plug 1 in and we get what? We get 3. How about the limit as x approaches 1 from the right?
3.
Okay, this time we're looking here, we'd be using the formula 3x, which would be 3. So what does that tell us?
The limit does exist.
Okay, the limit does exist. Limit as x approaches 1 of this function equals 3. Okay. And now, what can we say about continuity? Okay, all right. This does not equal f of 1. We said f of 1 was equal to 0. So most of this worked out, but that last detail did not work. So we would have discontinuous, continuous at x equal 1 because the limit does not equal the function value. And what type of discontinuity would that be?
Jump?
Is it going to be jump or is it going to be removable?
Removable.
Why removable?
They go to the same point at 3.
Okay. The limit exists. If we were to graph this, just do a real crude graph here. 5 minus 2x would be a straight line, and then 3x would be another straight line. It's going to graph like that. We'll have a hole in the graph at 1, 3. But f of 1 is down here at 0, so we'd have a point there. So just a quick crude graph to kind of explain. Because the limit exists, it will be a removable discontinuity. Now, for this to actually have been continuous at 1, what's one thing we would need to change here?
When it's approaching.
Okay. From the original function, what one thing could we change to actually make it continuous at x equals 1?
Is it greater than or equal to?
Okay, we could do that, make one of them greater than or equal to, or even the less than or equal to. Ultimately, what we'd be changing is this right here. When x equals 1, f of x would have to equal 3 to make it continuous. Okay. Now, I'm not going to throw that one at you on the test, but just kind of take it one step farther. That might be a good bonus question. But that's why we say it's removable, because we can replace one particular point and that would make it continuous. Okay? Okay. Looking at our worksheets, the actual first couple of worksheets were more an algebra review. I'm not going to have anything like that on the test. So we can say nothing like the evaluating functions or solving quadratic equations. That's more of algebra things we will need, and you'll be doing a lot of that. In fact, we've been doing evaluating functions, but we haven't really stated it that way. Solving quadratic equations will be something we run into later, more so than right now. But the next several worksheets have been the limits evaluating limits, and looking at the graphs, continuity. So that kind of takes care of the first several problems of the test. All of those kind of limit problems will be listed first. And then we started getting into instantaneous velocity or average velocity, slope of a line, slope of a secant line, slope of a tangent line, and the difference there. So questions on the test might be find the average velocity over a certain time interval. So average velocity over the time interval from 3 to 4. Now with that, you would be given the position function, and then you'd have to calculate average velocity. We'd have the distance traveled in that time period, P of 4 minus P of 3, and then divided by the total time, which would be 4 minus 3. So whatever the position function would be, calculate those and compute the average velocity that way. Slope of a secant line. Okay. And well, let's just stay with that same. Now this would be the x interval over the x interval from 3 to 4. Well, guess what? It's going to be the same calculation, just probably a different function, but it'd probably be f of 4 minus f of 3 instead of p. But calculation is exactly the same. You're basically finding the slope of a line through the point where x equals 3 and another point where x equals 4. So one of the harder things about this test will be recognizing what you need to do. And is it this? Okay. If it's over a certain interval, you're going to have 2 endpoints. So you'll need the idea of either slope of a line through 2 points or average velocity like this. Now the other problems we looked at were finding instantaneous velocity at, say, t equals 4. If we're only given one time period or one time, then that's where we have to use the limit. And this would be position function. So p of, well, t is specifically 4, but we'd have the 4 plus delta t minus p of 4, and then all over the delta t, and then go through all that. Yes, you are going to have to go through the long way. I'm not going to have a lot of problems that you'll have to do well, this is really the derivative, but whether it's instantaneous velocity or whether it's the slope of the tangent line, at x equal 4, or even if I give you the 0.41, well, you really only need x equals 4 to calculate it. And again, it's going to be exactly the same here. You can use delta x if you want. Some of the videos showed H rather than delta X or delta T. You can use H if you want as well. It all works out to give you the same answer. So,
The slope of the tangent line is the same as the instantaneous velocity.
yep. Which is the same as the derivative of the function
Okay.
at, say, x equal 4. Okay. So all of that, they're totally different applications, but they use exactly the same operation. And we eventually define that as the derivative. So, and in more general terms, not necessarily instantaneous velocity, but instantaneous rate of change, that means the same thing. Instantaneous rate, anytime you hear that, it's derivative. Slope of the tangent line, that's the derivative. So. And let's see, we looked at position of an object falling to the earth or being thrown up and coming back down. We also later on looked at the motion of an object horizontally. Okay. Well, same thing. Instantaneous velocity in that case was still the derivative. And in that case, though, we looked at, I think, that worksheet I gave you the derivative, so you didn't have to go through that process. But using the derivative as well as the position function, you could get an idea of what the motion of that object was doing. Horizontal line. So lots of things that we can do with that derivative. Shows up in a lot of different places. And, well, all of these we've been saying when x equal 4 or t equal 4, there will be at least one problem where you need to use the definition of the derivative to calculate the derivative function. So in that case, that's your definition in general, f of x plus delta x minus f of x all over your delta x. And then don't forget the limit. So it's going to look very much like this, except be in general the x plus delta x minus f of x. Little bit more work algebraically, but it's, again, the exact same process we've been doing. So that would be the derivative function. And then along those same lines, whether it's a linear function or a quadratic function or something like that, or maybe one of these special functions, we looked at what the basic form 1 over x or square root of x. That just, the procedure was the same, the algebra just got a little uglier. That's what we did the last worksheet yesterday. So might throw one of those on there, but I won't throw too many of that type on there. I do want you to get done on Monday. So I think that's pretty much all the types of problems we've covered. Any particular questions? Any specific problems you want to see? Okay, for vertical motion, we would basically be taking an object and either throwing it up, throwing it down, dropping it, whatever. The position function would be given to you, And let's say it's going to be 100 plus 20t minus 16t squared. Okay. Now, if we have several different values to find instantaneous velocity, you could go ahead and find the instantaneous velocity function and then plug each one of the values into the function. Or we could use the, if it's just one value, we could go ahead and plug that in. So let's go ahead and say what is the instantaneous velocity at t equals 2. It's not showing up on the screen. It's showing up on my screen, but so where we're given just one particular value, let's just use it. Technically, notation-wise, we're finding the derivative evaluated specifically at 2, and that will give us the velocity, the instantaneous velocity at 2 seconds. That's going to be the limit as delta t approaches 0 of p of 2 plus delta t minus p of 2 all over delta t. Okay. Now at this point, lots and lots of algebra to do, lots and lots of opportunities for little mistakes. Yeah, you remember. So
I have a question. Can you do like find the derivative first and then plug in the 2 on the derivative?
you could, yeah. What you would do is instead of the 2 here and here, you'd just put in t in general and then work through it that way. So should work, should give you the same answer either direction. So P of the quantity 2 plus delta T we would have this. Those are little deltas, not circles. Sometimes I get a little sloppy. Then minus, now remember this is minus that entire quantity. So we can put a parentheses there. Now when you're squaring the value, make sure and square 2, then multiply by the negative 16. Don't say negative 32 and then square it. That's going to give you way off. Okay. And then all over our little delta t. Lots of algebra to do. We'll kind of do a little bit of it here and then move to the next page. Sometimes if we do it in this manner, we can go ahead and calculate P of t by itself and get one particular number here rather than writing out term by term. Let's go ahead and do that. We'd have 4 times 16 is what, 64?
Yeah.
So 140 minus 64 would be 56?
Yeah.
Okay. So minus 56 on that part, and then here we'd have 20 times 2, 20 times delta t. This is really where most of the work gets done. So let's go ahead and jump to the next page. We'll take care of that and then kind of plug it back into where what we had. Now, we are taking a binomial and squaring it, so don't forget we've got to have that. So we leave the negative 16 alone for now, and we'd have 4 plus, well, we've got 2 times delta t plus another 2 times delta t. And then the delta t quantity squared. then multiply the negative 16 through. We'd have negative 64 plus or minus, get rid of that, 64 delta t and minus 16 delta t squared. Okay. So back to our original limit, we had the, you'll have to help me remember what those numbers were. Was it 100? Then we had 20 times the 2 and 20 times the delta t, and then all of this. And then finally minus the f of 2 or p of 2, which would we end up with 56 on that one? So 140 minus 64 is 56 minus 56. All the constants cancel out, and what we're left with then, which on all of these, all of the constants should go away. We've got a 20 delta t minus 64 delta t, so minus 44 delta t minus 16 delta t squared all over delta t. At this point, everything should cancel except for terms that have delta t in them in the numerator. Factor out a delta t, and that will cancel here. We'll be left with negative 44 minus 16 delta t, kind of run out of room, so shortcut notation. And then as delta t approaches 0, we're left with negative 44 as our instantaneous velocity. Unit-wise, that would be what? Okay.
You want us to put the units?
If there's units given, and in that type of problem we had feet and seconds, so negative 44 feet per second would be the instantaneous
When you
velocity.
have a question like saying, what is initial position? What is initial
What is
velocity?
initial position? What is initial velocity? Yes, that would be a possibility.
And
So
when they give you the slope and then you have to find the x and y, well, you have like to find the equation of the slope.
find the equation of a line,
Yeah,
possibly. Yeah, possibly that.
It's you use the slope
Yeah,
form.
point slope or
Point
slope intercept. Yeah,
Yeah.
that's a possibility.